When you look at a Linux system from far away, it can feel like a single computer doing its own thing, but as soon as that system needs to talk to anything else, it becomes part of a network of services that must cooperate. Those services are not only the big ones you hear about in security headlines, because the most fragile failures often happen in the basic plumbing that everything else assumes will work. Name resolution, time synchronization, automatic network configuration, basic web service behavior, and mail delivery are all foundational, and when they break, the symptoms can look unrelated and confusing. In this episode, we focus on the exam-level understanding of common services, domain name system, DNS, network time protocol, NTP, dynamic host configuration protocol, DHCP, hypertext transfer protocol, HTTP, and basic mail concepts, with an emphasis on what breaks and how those breakages show up. You are not learning how to build a full enterprise service here, because that is not the goal, but you are learning the mental model that helps you recognize service failures and reason about likely causes. If you can identify the kind of service in play and the typical ways it fails, you will be much calmer when a Linux system behaves strangely. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A helpful starting point is to separate services into two roles: services your machine consumes and services your machine provides. A workstation typically consumes DNS, NTP, and DHCP, meaning it relies on other systems to supply names, time, and network settings. A server might provide HTTP or mail services to others, meaning it must listen for requests and respond consistently. The difference matters because the failure story changes based on direction. If you are consuming a service and it fails, your machine may be correct but unable to reach the provider, or it may have the wrong settings to find the provider. If you are providing a service and it fails, others may not be able to reach you, or your service may be running but misconfigured in a way that makes it respond incorrectly. Exam questions often hint at this by describing who is complaining, the local machine or other machines, and your first job is to identify whether the system is the client, the server, or both. Once you place the system in that role, the troubleshooting path becomes much more logical. DNS is often the first service to understand because it is the translation layer between human-friendly names and machine-friendly addresses. When you type a website name, a host name, or a service name, your system needs an IP address to actually communicate, and DNS is the system that answers, what address should I use for this name? Beginners sometimes think DNS is only for the internet, but the same concept applies inside private networks where internal names must map to internal addresses. When DNS breaks, the most common symptom is that things fail by name but still work by address, which is a powerful clue. For example, if a system can reach a remote service using an IP address but fails when using the name, the network path might be fine and the name resolution is the problem. Another common symptom is slow behavior, because applications often wait for DNS timeouts before they give up, which can make a system feel sluggish. You do not need to know every file involved to reason about this, but you do need the cause and effect relationship between names, addresses, and the applications that depend on them. At exam level, you should also recognize that DNS problems can be local or upstream, and the difference changes what you would check mentally. A local DNS problem means your machine does not know which DNS server to ask, or it is asking the wrong one, or it is blocked from reaching it. An upstream DNS problem means your machine is asking correctly, but the DNS server itself is misconfigured, unavailable, or returning incorrect answers. The symptoms can overlap, but the context often reveals the likely side. If only one machine has the problem, local configuration is suspicious, while if many machines share the problem, the upstream service is more likely at fault. Another useful idea is caching, because systems often cache DNS answers to improve speed, and cached wrong answers can persist for a while, making a fix appear delayed. If you hear a description where a change was made but clients still go to the old address, caching is a likely factor. DNS is therefore both simple in concept and tricky in practice because time and caching are part of the story. NTP is the timekeeping service that makes sure your system's clock stays aligned with a trusted reference. That sounds boring until you realize how many security and reliability features depend on accurate time. Logs need correct timestamps to be useful. Authentication systems often require clocks to be close, and distributed systems rely on time ordering to coordinate events. When NTP breaks, the system might still function, but it can produce confusing symptoms, like log entries that appear out of order or security checks failing because a certificate appears not yet valid or already expired. Beginners often blame applications in these cases, but the root cause can be the clock being wrong. NTP problems can also show up as gradual drift, where the clock slowly becomes inaccurate, or as sudden jumps, where the clock is corrected sharply. Those sudden changes can confuse time-sensitive applications and make troubleshooting harder because the system's record of events becomes unreliable. At exam level, remember that correct time is part of system health, not a cosmetic detail. A useful way to connect NTP to what breaks is to think about trust and alignment. If a system cannot reach its time source, it may fall back to its local hardware clock, which can drift. If it reaches a time source that is not trustworthy, it may align to incorrect time, which is worse than drifting slowly because it creates confident wrongness. In secure environments, the time source is often treated as part of the trust boundary because time influences verification, auditing, and authentication flows. Even without diving into implementation, you should connect inaccurate time to symptoms like authentication errors, strange log timelines, and inconsistent behavior across machines. If you see an exam scenario where multiple systems disagree about event timing, or where security services complain about time, suspect NTP, or a broader time sync issue. You are training your pattern recognition here, because time issues can masquerade as many other kinds of failures. Once you learn to suspect time early, you save yourself a lot of confusion. DHCP is the service that automatically gives a machine the network settings it needs to communicate, such as its IP address, subnet information, and default route. Beginners often think of DHCP as just how a computer gets an address, but it is more accurate to say it is how a computer learns how to participate in the network. When DHCP fails, the symptoms can range from no network connectivity at all to strange partial connectivity. A system might assign itself a fallback address, which allows basic local behavior but not access to the wider network, or it might have an address but no correct route to reach other networks. Another common failure is getting an address from the wrong DHCP server, which can happen in misconfigured networks and can place a machine on the wrong logical segment. The result can be a system that appears connected but cannot reach expected resources, which is frustrating because it looks like the cable and wireless are fine. At exam level, you should recognize that DHCP is about more than an address. It is about the full set of network parameters that make communication possible. DHCP issues also create a class of failures where the network settings are inconsistent across machines, and that inconsistency is a key clue. If one machine has correct settings and another has strange settings, the DHCP lease it received may be different or wrong. If many machines suddenly lose connectivity after a change, the DHCP service might have changed what it is handing out, which affects everyone. There is also a timing angle. Because DHCP settings are leased for a period, so changes may not take effect instantly on every system. That can lead to a situation where some machines have old values and others have new values, producing mixed symptoms during a transition. For beginners, the important idea is to connect automatic configuration to the possibility of centralized mistakes. When a central service hands out bad information, it can make many clients look broken even though the clients are just doing what they were told. HTTP is the basic protocol behind web communication, but at exam level it is more valuable to understand what kinds of failures it produces than to memorize every status code. A web service can be down, unreachable, or running but returning errors, and those are three different stories. Down means the server process is not providing the service at all, so connections fail or are refused. Unreachable means the server might be fine but network paths, name resolution, or firewall rules prevent access. Running but returning errors means the service responds, but something about the content, configuration, or backend dependencies is wrong. Beginners often treat any web error as the same problem, but the presence or absence of a response is a huge diagnostic clue. If you can connect and receive a structured response, the service exists, and the problem is likely in configuration, permissions, backend connectivity, or content. If you cannot connect at all, suspect network, listening state, or access control before you suspect application logic. HTTP services break in predictable ways because they are often the front door to other components. A web server might rely on files it must read, a directory structure it expects, or a backend service like a database that must be reachable. If those dependencies break, the web server may still respond, but it might return errors, blank pages, or unexpected content. Another common cause of breakage is mismatched assumptions about host names, because web services may behave differently depending on the requested name. And if DNS changes or virtual host settings are wrong, the wrong site may appear. Time can also be involved when encrypted connections rely on certificates, because a wrong clock can make certificates appear invalid, even if the web service is otherwise fine. At exam level, your job is to understand that HTTP is often a symptom amplifier. It is the thing users see, but it reflects underlying health of name resolution, file access, application state, and network policy. Treating HTTP issues as a chain rather than an isolated bug is a strong beginner habit. Mail is a service category that many learners find intimidating, but at exam level you mainly need a simple mental model of how mail moves and what parts can fail. Think of mail as messages that must be accepted, routed, delivered, and sometimes retrieved, and each step can fail independently. A system might be able to send mail to an outbound relay but fail to deliver locally, or it might accept mail but fail to route it to the right destination. Name resolution matters heavily for mail because mail routing often depends on correct DNS records, and time matters for authentication and security checks. Another common failure is that mail is treated as blocked traffic in some environments. So network policies can prevent mail-related communication even if the server software is correct. Beginners may see a mail failure and assume the mail service is broken, but the underlying problem could be DNS, firewall rules, authentication settings, or even a full disk preventing message storage. At exam level, remember that mail is a chain and any weak link can stop the flow. When you compare these services, a pattern emerges that is useful for troubleshooting and for exam questions. DNS breaks tend to show up as name-based failures and slow timeouts, while direct address connections might still work. NTP breaks tend to show up as inconsistent timestamps, authentication oddities, and certificate-related complaints that feel unrelated. DHCP breaks tend to show up as wrong network settings, inconsistent connectivity, and a sudden wave of client problems after a central change. HTTP breaks tend to show up as either lack of response, which points to reachability, or structured errors, which point to configuration or backend dependencies. Mail breaks tend to show up as messages stuck in transit, delivery failures, or retrieval failures, with DNS and policy often playing major roles. This is not a rigid checklist, but it is a set of mental fingerprints. The more you practice mapping symptoms to service fingerprints, the less random Linux troubleshooting feels. Another key exam-level idea is that these services are interconnected, so one broken service can make several others appear broken. If DNS fails, web services may appear down even when they are reachable by address, and mail routing may fail because names cannot be resolved. If NTP fails, secure web connections may break because certificates appear invalid, and mail may be rejected due to time-based checks. If DHCP fails, the system may not know its gateway or DNS server, so it will fail to resolve names and fail to reach remote services. This interdependence is why basic services are so important. They are shared assumptions. Beginners sometimes chase the most visible failure, like a web page not loading, but the real cause might be time or name resolution. A calm approach is to look for the most foundational service that could explain multiple symptoms at once. To close, the exam-level skill you are building is not the ability to configure every service from scratch, but the ability to reason about what a service does, what it depends on, and what failure looks like when that dependency is missing. DNS translates names to addresses, and failures often look like name-based outages and slow delays. NTP aligns time, and failures often look like strange authentication and logging behavior that does not match reality. DHCP supplies network identity and routes, and failures often look like partial connectivity and inconsistent settings across clients. HTTP is a visible front door that can be down, unreachable, or misbehaving due to back-end dependencies. Mail is a multi-step delivery chain that depends heavily on correct routing, policy, and system resources. When you can connect symptoms to these mental models and remember that services depend on each other, you will be able to navigate Linux service questions with much more confidence and much less guessing.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.